Welcome. In the last section that we were discussing, we took the classical diffusion equation and we substituted a solution which was sinusoidal for composition, and the amplitude of the sinusoidal waves was time dependent. We substituted this solution into the equation, and from there we tried to see what happens to the amplitudes with the different wavelengths. So, that was the derivation I did, and towards the end of that derivation I introduced a relationship between mobility and diffusivity. I showed that they are connected through the second derivative of the free energy with respect to composition. Okay. Today I want to start by deriving how that relationship comes about in the first place. We will do that first, and then we will go back to the expression that we derived and we will discuss it and see where classical diffusion equation fails to capture what happens during spinodal decomposition, and that will automatically lead us to the first phase field equation, which is known as the Cahn-Hilliard equation. And so when I introduce that equation, that will be the sort of logical conclusion to this set of discussions, lectures that we have been having. So let us start by deriving the relationship between the diffusivity and the mobility. To do that, let me start with a different expression for the flux. Okay. We have seen that the Fick's first law, which gives a relationship between flux and the concentration gradient, it is something like this. So, J is equal to minus d del C. So, this is the so called Fick's first law. But now I am going to write a flux expression for atoms of component 1 J1, which is equal to minus, of course, NV, the number of atoms per mole, 1 minus C, which is the composition of A atoms obviously, V1 and dou mu 1 by dou x, where V1 is the velocity of atoms of component 1, right, that is at velocity of A atoms under unit potential gradient, right. So, per unit potential gradient, what is the velocity of type 1 atoms, that is V1. Dou mu 1 by dou x is obviously gradient on the chemical potential mu 1. Mu 1 is the chemical potential per atom. Okay. So, it might be a good exercise always to do a dimensional analysis to see that the dimensions on both sides are in agreement. I will leave that as an exercise to you. So, it will be a tutorial at some point for you to take an expression like this and put the dimensions for each one of the quantities and see what is the dimension or units of this quantity J1, which is the flux of component 1, atoms of component 1. In a similar fashion, we can write J2, which is nothing but minus NV, total number of atoms per mole, C, because we are looking at the 2 component 2 and the composition is typically the fraction of atoms of type 2 to the total number of atoms. So, composition C is always representing the fraction of B atoms. So, that is why it is C. V2 dou mu 2 by dou x. So, these are the flux. Remember, here also it is actually J2, and when we said the C, that is basically corresponding to the B atoms. Okay. So, this is the Fick's first law. Now, we are trying to write different type of expression, the reason being that we have argued and we have shown also graphically that connecting the atomic flux to concentration gradient is not always correct, because spontaneously diffusion happens to reduce free energy, to minimize free energy, and the correct quantity which represents that minimization is basically the chemical potential. So, the right way of representing atomic flux is to connect them to the chemical potential gradients. And we have also seen that when you connect the flux to chemical potential gradients, the constant that comes is the mobility, whereas the constant that connects the flux to concentration gradient is known as diffusivity. We are trying to find out the relationship between diffusivity and mobility. I have not introduced mobility yet, I am going to define mobility at the end of this derivation, but for now I am going to say that the flux of atoms of type 1 is given by, of course it is going against the gradient for the chemical potential, so that is why a minus sign is there and the chemical potential gradient is there, and the chemical potential gradient is multiplied by the total number of atoms and the composition and the velocity of that type of atoms under unit potential gradient. So, that is going to define the flux, and similarly you can define a flux for B atoms. So, you have a lattice in which A atoms are moving, B atoms are moving, so you have found out the flux for these two. We are going to define the flux with respect to a particular frame of reference. Okay, so, that is the next step. That particular frame of reference is known as a reference plane, it is called Matano interface. So, let me, okay. So, this Matano interface is a plane, okay, and it is a moving plane, okay, and this plane is defined in such a way that the net flux across this plane is 0, okay, for which the total flux. Okay. So, if you can identify a plane which is a moving plane with respect to which the total atomic flux is 0, such an interface is called Matano interface. So, I want to define the fluxes with respect to such an interface. Okay. This again is probably a tutorial that we can do at some point, is to show that if you want to define the flux of, say, for the B type of atoms or the 2 type of atoms, let me call that as J, because that is what is part of the classical fixed law. So, that J is nothing but J2 minus C times J1 plus J2. Now, why is this flux is this? Because we are trying to define the flux for atoms of type 2 with respect to Matano interface. Okay. With respect to Matano interface, if you do, this is the flux expression. This is what you can derive and show. So, we will do it probably as a tutorial, but for now you can accept that this is the flux. If so, then I can substitute, let me substitute for J2, J2 I said is minus NV C V2, because this is J2 dou mu 2 by dou x, and similarly J1 and J2 we have. So, let me also do that. There is a minus sign and there is a minus sign in the flux J1 and J2. So, I am going to pull that minus sign, I am going to put it with this. So, that is going to become C. So, C times NV times 1 minus C times V1 times dou mu 1 by dou x. So, that is this part J1, and for J2 we are going to have C NV times another C V2 times dou mu 2 by dou x, right. So, this is the expression J2 minus C times J1 plus J2 is this expression. Okay. So, now let me do a little bit of algebra. Let me pull minus NV times C out, common to all of it. So, then what do I get? I get V2 dou mu 2 by dou x minus, okay. So, there is this NVC which I have pulled. So, I will have C times V2 times dou mu 2 times by dou x. So, from here if I pull C and V, so I will get the minus 1 minus C times V1 times dou mu 1 by dou x, right. So, as you can see V2 dou mu 2 by dou x minus C times V2 dou mu 2 by dou x. So, you can pull V2 dou mu 2 by dou x together. So, that will be 1 minus C, there is 1 minus C here. So, let us pull all that together, minus NV C times 1 minus C, right. So, then what do you get? Because 1 minus C is gone. So, this is V2 dou mu 2 by dou x minus 1 minus C is pulled, V1 dou mu 1 by dou x. Okay. So, this is the flux. So, to remind ourselves again, what did we do? We took the, we know the Fick's law which is written for atoms of type B. The flux for atoms of type B is related to its concentration gradient, that is Fick's first law. But our interest is to connect the diffusivity which is relating the flux to the concentration gradient with mobility which connects the flux with chemical potential gradients, because that is the thermodynamically consistent way of doing this. Okay. Fick's law works in some cases, but this law, this new type of Fick's law that you can think of, always works, because this always is saying that the system will spontaneously evolve in such a way that free energy is getting minimized, right. That is from where we got this. So, we did all those free energy curves and we tried to show that even though it looks like uphill diffusion, if you look at chemical potentials, chemical potential gradients are in the right way for that diffusion to take place. So, keeping that in mind, so we are trying to define the flux for type 1 atoms or type A atoms, which is given by minus NV times 1 minus C, which is the composition of the A type of atoms, V1 which is the velocity of A type of atoms under unit potential gradient, times the chemical potential gradient, and the chemical potential is defined per atom. Okay. So, that is the reason why there is this NV, because remember the chemical potential was defined as the free energy, the derivative with respect to adding some number of A atoms or number of B atoms, that is what defined the chemical potential. So, and then if you want to make it a concentration gradient, if you want to relate it to concentration, then there is this total number of atoms that you need to multiply. Okay. In the same fashion, for the flux of atoms of type 2, then it is NV times C, which is the concentration of B type of atoms, V2 which is the velocity of atoms of component 2 or B type of atoms under unit potential gradient, and dou mu 2 by dou x. Okay. Now, these are the individual fluxes of A and B type of atoms, but I want to define the flux of B type of atoms. Okay. This is what my interest is. This J is nothing but a quantity, a flux which is defined with respect to what is known as a Matano interface. What is a Matano interface? Matano interface is a moving plane, and that plane is defined by this condition, namely that net flux across that plane is 0. If you try to define the flux for B type of atoms with respect to Matano interface, then that expression is given by this equation, which is that the flux is equal to J2 minus C times J1 plus J2. So, all that we did is to substitute the expression we wrote for J2 and J1 and J2 and did a little bit of algebraic manipulation. So, I pulled NVC first, and then I realized that the first term inside has 1 minus C common. If you pull 1 minus C, then it becomes J equal to minus NVC 1 minus C times V2 dou mu 2 by dou x minus V1 dou mu 1 by dou x. Okay. So, I am going to again do a little bit of manipulation on this. You will understand why and how I do the manipulation, and that is what I will do in the next part of this lecture. Okay. So, we are going to take this expression for the flux, and we are going to do a little bit of algebraic manipulation, a small manipulation, to get to a place where we get an equation which looks similar to the Fick's law, and then compare to identify how the diffusivity is connected to the mobility. Thank you.